video we're going to be looking at angular and linear velocity again. In the previous demo we looked at 2 points that were traveling on circles. If they have the same angular speed, they're passing through the same number of degrees per unit of time, or they're passing through the same radian measure per unit of time. Angular speed is represented in trigonometry with this symbol. It's the Greek letter omega. Angular speed or angular velocity is always measured in radians per unit of time, and when you see the Greek letter theta, it should remind you that you're using radian measure. Linear speed or velocity is what we've been using throughout our lives. Distance per unit of time is how we measure speed, miles per hour, feet per second, etc. Velocity equals s divided by t is a little bit of a variation. We're not using the letter d because we're talking about speed on a circle. And when we talk about circular distance, we use the letter s. Now, the letter s, as you remember, is the length of an arc. It can be a portion of a circle or several times around a circle, but it refers to circular length. Circular length is related to the size of the circle, which is indicated by the radius and the radian measure. So the length of an arc depends on these two items. Again, we've seen this previously. So what we're going to do is we're going to take this formula, v equals s divided by t, and instead of the s, we're going to replace it with r times theta, the radius of the circle, times theta, the angle in radian measure. So now we have v equals r times theta divided by t. And one last step, hopefully not to confuse you, is you should remember that on the previous page we talked about theta per unit of time, radian measure per unit of time, as being angular velocity, or omega. So if we want to, we can take this, change this one more time from this step, v equals r times theta divided by t, replace the theta divided by t with angular velocity, and now we have linear velocity equals the radius times angular velocity. And most of the time in real world problems, we are going to be calculating angular velocity before we calculate linear velocity. So let's talk about a real world problem. Let's say that you have a wheel that is rotating at 300 RPMs. This is an abbreviation for revolutions per minute. Now, it is a rate of some sort, but it's not really angular velocity yet because we have to translate revolutions, 300 revolutions, to radian measure. And since each revolution equals 2 pi radians, if we do this conversion, so the revolutions cancel out, we're going to get 600 times pi per minute, or, I'll be rounding up a little bit, 1885 radians per minute. Again, we don't have a unit of measurement that we can write for radians. This is our angular velocity. Now we're talking about a tire, a wheel, something that a vehicle is actually riding on. So what we'd like to be able to do is say, well, how fast could somebody be going on a road if they're traveling on a wheel that's rotating at 300 revolutions per minute, or 1885 radians per minute? Well, for that we'd need to know the size of the tire because that does have an impact. So we're going to say that the radius of this tire is 16 inches. And since we've already calculated our angular velocity, and again, theta divided by t, or theta per unit of time, is our angular velocity. Obviously now we can calculate our velocity by substituting in 16 inches for r and 1885 radians per minute for our angular velocity, and we're going to be getting our answer in inches per minute. And we will be traveling at 30,159 and 3/10 inches per minute. Not a standard way for us to measure speed, especially if we're traveling on a road. On the next page, we're going to be talking about conversion. Please understand, this answer is perfectly valid. It's in inches per minute. It's in linear distance per unit of time. So it's a perfectly fine answer, but we are going to be converting it on the next page. In our conversion, the first thing that we would probably like to do, and it doesn't matter what order we do these things in, but we like to change minutes to hours. So what we're going to do here is we're going to say, well, there are 60 minutes in every 1 hour. And the reason that we're doing this is because we want to cancel out the minutes. So when we do this, we get the velocity equals 30,159 3/10 times 60. It's going to be in inches per hour. We actually do that on our calculator. We get something enormous. However, it is just temporary. Inches per hour. Now what we'd like to do is change the inches to miles, because again we're looking for that standard measurement of speed that we have found on the road, and it's going to be miles per hour. So please look at what we're going to be doing here. We have inches per hour. We'd like to get rid of the inches, so we're going to put 12 inches here, because there's 12 inches in every 1 foot. There's 5,280 feet in every 1 mile. And the reason I'm kind of showing you this is to illustrate that when we're doing these conversions, we have to have units of measurement that we want to cancel out. They should be on the diagonal. Here our inches are going to cancel out, and then our feet, leaving us with miles per hour. Now what we're actually going to be doing with these numbers is we're going to be taking this number and we're going to be dividing by 12, and then if you break it into 2 steps, if you hit enter on your calculator at this point and then divide by 5,280, you'll get your correct answer. So you're really taking this number, dividing it by 12, taking that answer and dividing by 5,280. Since we're using calculators, I think that's probably the most efficient way to go about this. Our answer is 28.6. Again, it's in miles per hour. It's a reasonable answer. And again, this is just a conversion of one way of measuring velocity, which was inches per minute, and changing it to something that's more useful to us in real life, miles per hour. We've been talking about angular and linear velocity.